So today we're going to study matrices. We introduced the notion of a matrix, which we kind of already used in the topic of Gaussian elimination or row operations beforehand. But today we define formally what a matrix is, at least for our purposes. And we're going to talk about standard notations, and we're going to talk about also operations with matrices. In this case, just addition and scalar multiplication, which is followed by matrix multiplication, which we'll talk about a little bit in more details next lesson. And even for such a basic thing that everybody kind of already knows what it means because we already used it, I'd like to actually start with some real life motivation, because the reason we study matrices more formally is because they appear in many contexts, not just solving systems, as you will see later. So, you can deal with system of inequalities, and when you apply what we call later the simplex algorithm with some modification, you end up again with a big matrix and then with some row operations to deal with, again, in a different context. So what is a matrix and what's one of the motivations for it? Well, a matrix, you can take a moment and write down the definition. Here it's simply an array of real numbers. So basically a collection of real numbers that are arranged in rows and columns. So you can think of it as a two-dimensional objects, if you want, in the sense that, and we can write it down, each element in this array, in the matrix, is identified uniquely by its row and column. And again, by convention, in this order. We always specify the row first, and then the column number. And then let's give a little, like I said, little motivation why matrices appear naturally in many applications. So suppose, for example, you have two individuals that want to track their nutrient intake. Let's say they want to look to see or to count the amount of the grams, if you want, of proteins, fats, carbohydrates. So matrices actually appear naturally when you have multiple entities that have multiple characteristics. That's the typical application from real life that leads to matrices. Because how would you arrange this information in a natural format or efficient format, if you want? It leads to essentially a table of values, because you have these two characteristics, right? So you have the different individuals, and you can arrange them by rows, and then the characteristics, in this case, the nutrients, proteins, fat, and carbs, arranged by columns, for example. So for instance, for a day worth of tracking the meals, let's say two individuals, let's call them Anne and Bill, would like to, like I said, trace their intake of proteins, fats, and carbs. So automatically you end up basically with a matrix or a table with 2 rows and 3 columns. And let's say, just to put some random numbers here, let's say 20 grams are the proteins for Anne, then 10 for fat, and then 5 for carbs. Forget about any medical relevance to these numbers, because I don't know if that's realistic. And then Bill, let's say it has 15 proteins, 15 grams of fats, and then let's say 4 carbs. Now, obviously, as we move to more efficient way of writing stuff in math, once we know the meaning of the rows and the columns, we will write the same information just by listing the entries. Now, of course, we want to be efficient and not write more than necessary, but then it's our responsibility to know that the rows stand for the individuals, right? Individual 1 and 2, and Bill in my case, and the columns stand for the nutrients. So if I do word problems with matrices, I better know the meaning of the columns and the meaning of the row, of each row, and then I better write them down just to make sure I don't forget the meaning. Typical notations of matrices is with capital letters, so you can call this matrix A. And often is necessary to specify or to at least be aware of the dimension of the matrix. So the dimension is the number of rows versus columns, or the type of the matrix. I'm going to use actually this word more often. So what type of matrix do I have in this example? Well, A is a 2 by 3 matrix. By that I mean 2 rows and 3 columns. You always specify the number of rows first and then the number of columns. That's important to keep in mind as a convention, because then in some applications you'll have to check quickly the number of rows and columns of various matrices in the same problem, because they have to be in some sort of agreement before you can do that operation. So to follow up my example here, sorry, sometimes there are random messages here because I'm using a tablet to do this. So I'm recording the screen. And if we follow this example, let's say I look at day 2 of the same type of information. And then in that day, let's say Anne and Bill will have a different setup of the nutrients intake. So again, these are proteins, fats, and then carbs. And let's say in that day we have 5 proteins for Anne, let's say 5 fats, 2 carbs, and then let's say, I don't know, 10, 2, and 5. Again, I don't know, put too many 5s. Anyway, I don't know if that's, like I said, if that's realistic, but let's call this matrix B. So it's going to be 5, 5, and 2, 10, 2, and 5. And again, obviously, this is still a 2 by 3 matrix because, after all, it depicts the same type of information. For the 2 people, the intake of proteins, fats, and carbs in a given day. So I'll actually move on the second page with a formal notation of a generic matrix of m rows and n columns, because there are some notations to keep in mind when you write down generically an element in the matrix. But right now I want to still stay just a little bit more on this example to show you how operations of matrices also are not just for the fun of it, because that's another thing, especially when we move on to matrix multiplication. That's what I want to really emphasize, that all of these operations are not invented for nothing. They actually respond to, sorry about that, they respond to real life applications. They respond basically to applications not just from the real life problems like word problems, but also from other branches of mathematics. For example, matrix multiplications can be related to some geometric properties, for instance. But in this example, let's say here's a justification for addition of matrices, which I'm going to introduce later. Let's say Anne and Bill want to basically have the information about the total intake for 2 days. So the intake of these nutrients for 2 days. And they still want to have the information broken down by category, right? I mean, proteins, fats, and carbs. Well, obviously you just have to add. But how do you keep the same category separated, protein, fats, and carbs? Well, you're just going to have to basically add these terms item by item corresponding for each row and column. So when you take the first matrix and the second matrix, if you add these matrices term by term, you basically add the nutrients per category, right? So 20 plus 5 is going to be carbs in day 1 plus carbs in day 2 for n, right? So the meaning of this element on the row 1, column 1 is the protein intake in 2 days for n. And then you can continue 10 plus 5, 5 plus 2, 15 plus 10, right? So that's for Bill, right? I mean the protein intake in day 1 for Bill, and then day 2, and then for Bill 15 plus 2, right? The fat intake, and then 4 plus 5. Okay, so the matrix addition, which is one of the most basic operations and kind of like an intuitive operation, right? Because it's because it's intuitive to add the elements term by term for each row and column. Some other operations are not that intuitive, but they still have a very good reason to be defined that way. So 25, 15, 7, 25, 17, 9. Here's an example, like I said, of a matrix operation, which is matrix addition, again, to be defined on the second page. And let's actually squeeze one more example, and then we'll abandon the Ann and Bill and their food intake. Let's say Ann, or let's say both of them want to double the intake of all nutrients. Okay, so if they want to double the intake of the nutrients, well, you just have to multiply by 2 all elements. And so that stands the reason that I can define, for example, the multiplication between a real number and the matrix. This is what we're going to call later scalar multiplication. So if I want to double the intake in day 1, I can define this operation, a matrix times 2, which essentially means multiplying by 2 all entries in the matrix. 2 times 20, 2 times 10, 2 times 5, 2 times 15, again 2 times 15, and 2 times 4. And that'll give me 40, 20, 10, 30, 30, and 8. So I hope this motivation is good enough for you to understand that all of these operations have a reason to be defined that way. And let's move on the second page to actually have a generic notation for a matrix of n columns and, m rows and n columns. Let's see. So how do you denote a matrix, and especially its elements in the matrix? Well, the convention is to use basically what we call a double index. So for instance, to pick the example from last time, if you want to denote each entry by a variable, you would use typically a variable letter identical to the matrix letter, but in a small letter, let's say small a in this case. And with 2 indexes, you indicate the row and the column. So each element is going to be written as A sub I and J. So that's not multiplication, that's just double notation, where I is the number of the row number, and J the column number. So in this case, for example, A12 is 20, A11 is 20, A12 is 10, A13 is 5. You only specify the row first and then the column. So because I wrote all the elements in a given row, obviously the index was the same, the first index, 1 in this case. Let's say you want to write the column 2 entries in the matrix. Well, one of them is already written here, A12 equals 10. The next one is going to be A22, which is 15. So row 2, column 2. Let's write the last column, row 2, column 3. So that will be A23, which is 4. And obviously the first entry on the second row will be A21 equals 15. Row 2, column 1. So in general, and we're not going to use actually this generic notation for too often, but except in some particular cases when I want to describe a certain property or definition, we may need to actually have an efficient way to write a general matrix of m rows and m columns. So let's say, I have a matrix of m rows and columns, where m and n are positive integers, obviously. Then you can write, if you have to, obviously, you can write the matrix by specifying a couple of rows. So for example, row 1 will be A11, A12. Then you can write a generic middle point here, A1, or middle entry, A1J, and then A1N. So if you look at the second index, that's going to be going from 1 to n, because I specify n columns. And then you can write the second row, A21, A22. Right underneath this guy is going to be A2J, right? So obviously, when you go by column, the second index is the same. Then if you want, you can write a generic row, AI1, AI2, and then of course, in the middle, the generic entry, row I, column J. And then later on, the last row, of course, is going to be a M1, right? So the row will go from 1 to M, M2, MJ, AMN. We're not going to do this too often. Most of the time, once we understand how this notation work, so this is an M by N matrix, we can do a shortcut here and say A is described by Aij with I going from 1 up to M, J going from 1 up to N. So this is what I'm going to use quite often when I have to refer to a generic matrix. I'm just going to basically write the typical entry, the generic entry on a certain row, right? So row I and column J. And I'm going to just specify, of course, the range for the column index and the row index, 1 to M and 1 to N. Often you have the same number of rows and columns. So if M is equal to N, we call this a square matrix. And now the example before, of course, was not a square matrix, but here's an example of one. So let's say matrix B is given by -1, 2, 3, 5, 0, 1, 1, 2, 0. This will be a 3 by 3 square matrix. And for example, the element, just to practice, element little b, let's say B is given by little bij. Little b of coordinates 2 and 3. That means row 2, column 3, B23 is equal to 1. So let's finalize with a generic definition for these operations that I mentioned before, and we finish up with some examples. And we're going to do that on the next page. All right, so matrix addition. So in this case, we need two matrices of the same number of rows and columns. So take a moment to write this down. Matrix operations require a certain condition on the number of rows and columns. You cannot just add any two random matrices. So in this case, we need the same number of rows and columns for two matrices. So suppose I have a matrix A and a matrix B given by these generic elements, Aij, Bij, and let's say, like before, I goes from 1 to M, J goes from 1 to N. So the sum of the two, so the sum between A and B, so the addition of these two matrices, is a matrix C whose elements are given by Aij plus Bij. Okay, so A plus B is a matrix C, which is described by, let's say, Cij, in which Cij is equal to Aij plus Bij. So this is actually maybe fancier than it really needs to be, because we kind of have to describe the definition in generic terms. But once you see the example, like you saw the example before at the beginning of the class, this is nothing but term by term addition. And it makes sense why you need to have the same number of rows and columns so that you can pair these terms with each other. So for example, let's say I need to add the matrix 2, minus 3, and 4. Let's actually write this down, write down some notations here. So let's say we have a matrix A given by 2, minus 3, 4, 0, 2, 1. B, let's say, is of the same type with entries 1, minus 2, 0, 5, 1, and 2. And then C equals minus 3, 0, 5, and then 2, 1, 3. All of them are 2 by 3 matrices. So I can add them together. So for instance, I could do A plus B. And feel free to do it in your mind. You don't need to show extra work on this. Here I'm going to write down again intermediate steps just to see where they come from. But of course, get ready to do this a little bit faster and in your mind, because this doesn't necessitates any scratch paper, right? Once you understand what you're supposed to do. So term by term addition, 2 plus 1, minus 3 plus minus 2, pay attention to the signs there, 4 plus 0, 0 plus 5, 2 plus 1, and 1 plus 2. And then of course you don't leave it like that, you're going to simplify it. So 3, minus 5, and 4, 5, 3, and 3. Another operation for today's lesson, which again I already alluded to it via an example, is the so-called scalar multiplication. I'm not going to spend too much time in actually talking about this word scalar, what it means. Let's just basically equate it with a real number. Because if we see these matrices as entities that can be computed via various operations, it's a good thing to somehow distinguish the actual numbers to other types of elements that can be added or multiplied, like matrices. A much more honest and deeper definition, well, correct definition if you want, of the word scalar is better understood if one studies vector spaces, but that's not our focus for this class. So the scalar multiplication is simply to make no confusion between just multiplication of matrices, because there is a way in some conditions on how to multiply matrices, which we will cover in the next lesson. But for now, if you have a real number, so given, let's say a real number, and the matrix big A, let's say given by the generic element Aij, it can be of any type, then little a times big A is the matrix obtained by multiplying Aij by A. Okay, so as a matrix, little a times big A is given by little a times Aij. That's the generic element. And like I said, we had already some examples before. Let's do another one, and we're going to finish with another example that combines these two. So let's say with the examples above, I want to do 3 times b. Again, feel free to do it in your mind, but all you do is you multiply by 3 all entries in that matrix. And then simplify. So it's 3 minus 6 and 0, 15, 3, and 6. Just like operations with actual real numbers, for now, and take it for granted that, because one can actually prove this, but take it for granted that the order of operations actually is kind of similar to the order of operations for real numbers. So you can combine various operations, you can use parentheses, and you can proceed in the manner you will do with real numbers. So for instance, and let's finish with this example, let's say in some problem, I want to compute 4 times C plus A minus B, where A, B, and C are the matrices that I mentioned above here in this page. So what would you do first? Well, obviously you will actually multiply C by 4 and you will recognize that scalar multiplication. Then you can do this together and then you combine into another addition. By the way, I didn't mention this subtraction thing, but subtraction is just like real numbers. You multiply B by -1 and then add. So, you know, the subtraction of, I'm numerated here in this corner here, the subtraction of two matrices, you can basically think of it as scalar multiplication by multiplying to -1 all entries and then adding to A. It doesn't have to be called a new operation. Or if you want, it's an operation just like addition, but you subtract the entries term by term. So let's actually plug in these matrices and let's exaggerate the number of steps, because again, I'm perfectly expecting you to do this a little bit faster. Maybe one intermediate step, but more than one is not enough. It's not necessary. So I'm plugging in now the matrices. So 4 times C, the matrix is -3, 0, 5, 2, 1, 3. And then the matrix A, which was 2, -3, 4, 0, 2, 1. And minus B, which is, let me see 1 second here, because I want to make sure I don't miscopy here. So minus B, 1, -2, 0, 5, 1, and 2. All right, so like I said, let's do the scalar multiplication first. That gives me 4 times -3, which is -12, 4 times 0, 4 times 20, 4 times 5, which is 20, then 8, 4, and 12. There's that, and then let's do the difference between A and B. Here again, we have to pay attention to the signs. 2 minus 1 is 1. -3 minus -2 makes it -1. So it's -2. 4 minus 0 is 4. And then 0 minus 5, it's -5. 2 minus 1 is 1. And then 1 minus 2 is -1. And then we finish with matrix addition. -12 plus 1 is -11. 0 minus 1. 20 plus 4, that's 24. 8 minus 5 is 3. 4 plus 1, and 12 minus 1. Okay, so I realize that again, this is the basic stuff, and if you're really comfortable, and especially if you did matrix operations before, because the class doesn't assume you did that before, that's why we went over all these details. If you did it before, you can go a little bit faster and even skip steps if you want on this lecture. Just make sure you understand the motivation to begin with, and then be comfortable to do these matrix operations and get used to the notation. So for the next lecture, we're going to talk about the matrix multiplication, which for that, again, I like to take my time to give a motivation for why it's defined the way it is. It's a little bit more practice needed in that case to do the multiplication quickly and correctly. So that's it for today.